So if you go into the Moodle course that we've set up for this class, there's a Desmos slope field generator link, so click on that and you get into Desmos. And so they've programmed this graph software to graph a differential equation, dy over dx. So if you remember, our differential equation was k times p times 1 minus p over n, but p was my dependent variable, so we could go k times y in this case times 1 minus y over some value of n. So that is my differential equation, and we could let k go from 0.3, 0.2, and n we could make a slider. N could be the carrying capacity, maybe it's n is 10. The one thing with Desmos and with most of these slope field generators, they don't go too far. You can't see too much. It's not going further than the standard window of -10 to 10, because they're actually quite complicated to make. So I'm going to actually make n like 4 so we can see the effects here. So think of k as 0.2, my rate of growth is 0.2, my carrying capacity is 4. This is my slope field. So what is a slope field? It's a plot of the slope for different values of y and x. So let's say I plotted the point x equals 1, y equals 1. We have this little slope here, depending on what k and n are as well. So we have this slope, which is going to be whatever that is, 0.1 or 0.2, and so on. And we notice our equilibriums happen at p equals 0, which is here. We have a horizontal slope, and p equals 4, which is my other equilibrium, which is the carrying capacity. So p, remember, this is the p or the y-axis, and here's the x-axis. So you notice no matter where I start here, curves kind of go through an initial value and then will curve up to that equilibrium value. So in between 0 and 4, all the solutions kind of curve up to that, from the y equals 0, p equals 0 to y equals 4, p equals 4. If you're above 4, it's curves down. So each of these describe a solution curve. Each of these describe a solution curve to my differential equation. They're each unique, so they're not going to touch. And again, if you start at a negative p or y, you slope downwards away from the equilibrium. So this equilibrium at 0 is called a source. Equilibrium here at 4 is called a sink. Now what if I wanted to plot this in a program called Matlab, the same logistic function here, and I've changed k to be 0.1 and n equals 10. So we use this code here. This code has all kinds of syntax, so just you might want to copy and paste most of it, and the only thing you need to worry about really is the window here. So the windows I've made from -5 to 30 for both the x and y axis. Remember, x and y translate to t and p in our equation, and then the 1 here, the value in between the minimum and maximum values, is actually going to determine how big your arrows in your slope field is going to be. Here's my equation, my logistic equation. If you look at it, that's my logistic equation. That's the only thing you want to change if we're changing the function, and the rest of this stays the same. This quiver, this final thing is a quiver. It makes an arrow plot, and this kind of standardize, these two commands here standardize the size of the arrows. So we're going to look at Matlab. We're going to copy and paste this into Matlab. So here we are in Matlab. Once you open it up, you get this prompt here. I've copied that code and I pasted here, and remember, it's that logistic function with k equals 0.1 and n equals 10. So if I hit enter on this, you see this plot here. If we expand this, you can kind of see here at 0 we have equilibrium, so all the solution curves, no matter where I go, kind of move away from it. And then n equals 10, again it's a horizontal line, so all the solution curves go towards that. And if you start above 10, you go down towards there. So I can actually copy and paste this. If I go edit and copy figure, and we put this in a Word program, like this here. So we have this in wood, and so let's say we started this at an initial value here of let's say of around 3 or so. What happens if I follow the arrows? You kind of get the solution curve here. So the arrows kind of point you where to go, and eventually you end up there, close to the equilibrium. But if I start here at the initial value of 25, let's say, well, I follow the arrows down, and then I get another different solution. And again, this is the existence and uniqueness theorem. It's showing me each solution is different. They exist, these solutions, and each solution is different depending on my initial value. Or if I start here a little bit higher than 5, well, if you follow the arrows again, it kind of shows you, kind of takes you to equilibrium again. And if I start below 0, here's another solution. It's going to take me down here like this. So this is the slope field, and without even solving this equation, we can see the behavior of solutions. So this is 0.1 p times 1 minus p over 10. So without even looking at the solving this explicitly, we can see the behavior of the solutions looking at the slope field.